Hi, everyone. So Lime sent me here today to talk about some drivers and the ecosystem we created. And now I'm not here just to talk about Lime-related stuff. Basically, over the years, we've made a number of, I think, things that are basically useful to the SDR community in general. I'd like to talk about it. Basically, if you're using an SDR, I think this talk's for you. And if you're creating an SDR, I think this talk's also for you. So let's get into it. Introductions. I'm Josh Blum. If you don't know who I am, you've probably used something I've created. So back when I was doing my bachelor's degree many years ago, I did GRC. I've also been involved with UHD. I've done drivers, firmware, FPGA design. The USERP 2 and N210 was one of my favorite boards. I did a whole bunch of packet routing and network framing on it. It was a ton of fun. Volk, I got involved with not doing actually any kernels, but a lot of the code generation, the architecture selection. So if you understand why I enjoy that, you'll understand why I'm doing talk about drivers now. Currently, I'm the maintainer of SoapSDR, something we'll get a talk with, and the Pothos data flow framework. Recently, I've been involved with the LimeSDR crowdfunding campaign. Maybe you've heard of that. And I've done a number of not just driver work, but demos and blogs to go along with it. And finally, I'm also active on MyriadRF for packaging, where we manage drivers and GNU Radio packages for the community. But I have a day job, and so what I do, I'm an embedded engineer at Skylark Wireless. Essentially, we're a startup, and our goal is to serve underserved communities or rural communities that don't yet have access to broadband. So our goal is to create wireless nodes using Lime RFICs to serve these communities using massive MIMO or multi-user MIMO technology. See more in the link below. And my job there is basically a jack of all trades. I bring up boards, calibration, testing, FPGA design, kernel modules, a bit of everything. It's a startup, that's the kind of thing we do. So, getting started. Drivers and APIs. SDRs are great. SDRs are exciting. You get to communicate over the air, over the radio waves using software, and I think that's amazing. But under every good SDR application, there's a boring, tedious driver sitting underneath of it. So we go to use a driver, we need to make an application. We have to choose languages, we have to choose APIs, we have to read the documentation. There may not even be documentation, compilers, debugging. So in general, this is something everyone has to do. We don't like to talk about it, it's not that interesting, but we're gonna go into it. But drivers, why do we do it? Well, in general, it's a good idea to encapsulate functionality, to save developers time and confusion. Nobody wants to interact with a device and, which SPI register do I set? What's going on in this register bank or this I2C? You actually want high-level controls, and this is an important part of abstraction. So I want to set my gain in dB and my frequency in hertz. I don't want magic byte offsets and bits and bytes interleaved. Give me samples to work with, samples and flags. And further, I don't know about your brain, but I have a memory allocation error. I don't have enough RAM in my brain, and I can't get everything in at once. So we need to compartmentalize problems and split them up in ways that make sense so we can go about our jobs and make compartmentalized pieces that are easy to test and work with. And finally, abstraction, another important part of drivers. You wrote code, now you change it a little. You need a different device, there's slightly different controls. Do you copy and paste all of that? Or do you realize you have a pattern and you start making something more general that's parameterized? So this is the kind of game we have to play. So anyway, I know this is a software-defined radio, so I don't think I have to sell you on good software paradigms. Just wanted to set up the framing for the rest of the talk. So let's talk a little bit about a story. In 2014, I had a problem to solve. I needed generic SDR support. I wanted to bring SDR's source and sync streaming to my new data flow framework. And I was like, I want to support most, if not all, SDR devices. I don't want to do a lot of work. I want to be able to just talk to any SDR out there, RTL, HackRF, whatever. So I looked at what was going on in the market, the projects on GitHub, et cetera, and I kind of noticed a pattern. Everyone was sort of pulling in, a C driver here and a C driver there, and whenever a new device came on the market, you'd have to go wrap it up again. Every time it would be a slow sort of pace where people gradually waterfalling different drivers into their system. And it's a lot of duplication of effort. And two, we get a lot of different implementations. Suppose you have an application that's not interested in transmit. Well, you're going to go wrap up receive only. You're going to do it only in the way you're interested in with just the controls you're interested in. And so I want something more generic than that. Now, Reusable SDR is very good. It's very close to this. It's well maintained. It's got nearly every, it's got a well-defined API, nearly every C driver wrapped up into it, which I think is great. It's got a few downsides. It's a hard sell. It's very massive. It pulls in LibBoost, GNU Radio, Volk, and everything under the hood. And it's hard to say, hey, I just want to get access to some controls and some streams, but you're going to need to compile this gigantic thing and pull in these huge dependencies. That's difficult. Another thing is streaming API. Reusable SDR was set around connecting GNU Radio blocks to interface with the stream, which is really good for GNU Radio, but sometimes I just want to write some code where I can read and write a chunk of samples. And that's kind of abstracted and taken away from the user in terms of this GR block streaming API. So that's sort of what we're faced with. Oh, and further, it's sort of difficult to do high-level things we want to do with timing and bursts. And so that was also a consideration. I want to make it easy to not only request bursts, but to transmit stuff at particular times. We need high-level stream controls. So here's what I was thinking. I see a problem in the community. I have a problem I want to solve myself. Let's make a framework. What are we going to do? What are some requirements? So I want to make an API that anyone can use, not just me. I want generalized support for a device, so I can say, what devices are on your system? Identify them. Give me a name. I need to know what they are. Generalized settings. Pretty much everything you want on SDR, there's a lot of common patterns here. Frequency, gain, I want to set and get that. Rates, filters. Sometimes more advanced stuff, sample rate. Also, we need a streaming API. I need to be able to read and write chunks of samples. I want to support metadata and advanced burst controls and time controls. And finally, minimal dependencies. So ideally, I want you to be able to take this framework and just with a compiler be able to build it. Sure, if we pull in additional hardware here or there, you're of course going to need their driver library. But minimally, you should be able to just build this framework against your application, and that's it. So follow that up. I want this to be a module or plugin based architecture. That means once everything's installed, hardware modules are essentially files that support your particular piece of hardware, and you install them after the fact. And the driver API basically says, if I find this on my system, I'll be able to talk to him, I'll be able to enumerate devices, I'll be able to tell you about it. So this is how we can build applications off a very simple, sort of simple API. and then we can basically query everything later. And finally, I want to do permissive licensing. I want everyone to be able to use this new framework I'm going to make, whether it's open source, any of those licenses, or commercial, or private or public use. We just want to make sure you can use it. So, fast forward, now we have something called SoapSDR. This is what I put together to solve our framework issue. So, we've got a C++ and C API. So, you're very familiar with that. And of course, Python API, which is great. Everyone here loves Python. I love Python. The best thing about Python is I can go ahead, I can immediately just type off in my Python terminal, open a device, configure it, see what's on there. It saves so much time. Second of all, very low boilerplate. I want people to be able to create, essentially, support modules underneath this system. And so, in reality, we provided a CMake macro, and you just make a very simple CMake macro, call this macro with your source files. Generally, there's 3 files, typically a settings, which is your get and set frequency, fill it in, call your underlying driver. Streaming, how do we read and write sample streams? And registration, how do we find the device? Most, if not all, of the SoapSDR projects basically look like this. And I can report now, as of this presentation, that nearly all of the major SDR devices on the market actually have SoapSDR support, which is amazing. Special thanks to Charles J. Cliff at Cubic SDR, because he actually stepped in and produced a bunch of these, because he had the same problem I did, is he needed to make an application and bring in SDR support. So this is clearly a niche we needed to take care of. So some interesting things about SoapSDR is on top of what I just talked of, we have some neat modules. One of them, Soapy Remote. So this means any device that you've built into SoapSDR, you can now run the Soapy Remote server on one end, and you install Soapy Remote on a host or PC side, and it transparently just shows up on your device. Soapy Remote takes care of all the tunneling for all the network controls and all the streams, and we try to do a high rate streaming windowed protocol, and we talk TCP for all the basic controls. And so it's very transparent. Same API, whether it's Python, C, or whatever, works. And this has been very popular with some of the embedded ARMs where you can plug in something like an RTL and get about 2 megasamples a second. We can certainly do better with a bigger PC, but that's just been a pretty popular use case to get a quick sample stream over TCP for just about any device. We also have SoapSDR multi-SDR, and basically this is just a simple way to put a homogeneous group of devices into a single device handle with much wider channels, because some people want to work with an API where there's just many channels in one device. And finally, because sometimes we have a module very soon when a new hardware device comes out, and sometimes GR-Osmo SDR actually does, I've created SoapSDR, which is essentially a project that can pull in the implementations inside GR-Osmo SDR. Now, we don't pull in all of GNU Radio. We basically pull in the wrapper layers that talk to the underlying C library, and we build them into this project. It basically only pulls in Boost and whatever libraries were needed. I do need a water, by the way. If anyone could. Thank you. So I wanted to bring up some interesting use cases or idioms that came up now that we have this great tool. And one of the things you can do is, whenever anyone makes a new device, they basically make this low-level C driver and ship that out and install it. But one of the neat things you can actually do is never have this low-level C API. You can actually build your entire module into a SoapSDR, or entire driver into a SoapSDR module. Thank you so much. We have more humidity where I'm from in Houston. So no C API whatsoever. And this is pretty powerful because it means you can rapidly make a device, basically fill in hooks for streaming settings, and have it work in Python, have it work remotely. This is great when you're making a device, let's say it's on a Zinc, and maybe your application is running actually on the ARM, and he's responsible for like controls and stuff, and high-level controls, hitting registers, bumping SPI, things like that. And further, with SoapSDR, we don't hide anything from you. So this actually gives you access to SPI, I2C, UARTs, and we have an API for generic settings. We really don't want to ever hide anything, so we can get access to anything you basically need on the chip so long as you fill the hooks in. In fact, not only am I using this at my job at Skylark, but there's some people in the room who are also actually making use of this feature with SoapSDR for their hardware. Thank you. Also, sample streams don't have to be just raw sample streams. The streaming API is actually capable of supporting things like packets and bound arrays of bytes and FFTs. We have the correct flags to deal with that. So in your FPGA, you may not have raw stream data. You may have a decoder, you may have an FFT, and we support that use case as well. Another neat thing that came up is there's a hybrid approach we can do here. And we did this with the Skylark Iris hardware that I produced. Basically, it was really nice to make an application that ran on the Zinc to give us control of everything. And it was really nice to be able to test that and get burst in and out. We brought up all the hardware that way. We couldn't do high-rate streams over the Ethernet. The ARM's just not capable of it. But there's a hybrid approach where we used all the stuff we wrote with SoapSDR, SoapSDR Remote, and we basically filled in the hooks a little differently for the streaming because we needed hardware acceleration. So it's possible to have the best of both worlds and just do the extra work you need to get the hardware streaming going. Everything else is already handled by SoapSDR Remote. And finally, closing the loop. I think this is pretty interesting, but you can now make a device. It can work under SoapSDR, but we've also made a SoapSDR module for GR-Osmo SDR. So that means anything that's supported under SoapSDR, you don't have to go make a new Osmo SDR module or anything like that. It just works so long as you've compiled it in, and any application built on GR-Osmo SDR, quite a lot, like GQRX and GRC, just works. This is actually how we have support for LimeSDR and other stuff under LimeSweet software working within the GNU Radio environment. Also, just like there's a SOAPy UHD, and I know this is confusing, for supporting usurps under the SoapSDR, we've done the reverse. We've also made UHD SOAPy, which is for supporting SOAPy-supported drivers under UHD. And this is really nice because, of course, there's a lot of stuff written against the UHD API. So now if you have something supported under SOAPy, it will work in UHD. Further, everyone benefits from open source software because what's really nice is a usurp user can go run SOAPy Remote Server, and he can go over to his host PC, and he can run UHD API and transparently use his usurp over the network with SoapSDR in the middle, never having actually touched it, which is pretty amazing. And one more story on that point. I was following the HackerOff mailing list, and someone said, I can't UHD usurp probe or UHD find devices my RTL. Might have been Hackraft, might have been RTL. And someone had to explain, well, that's the wrong driver. But my reply to him is, you can do that now. So please feel free. You should be able to UHD usurp probe your RTL SDR. Okay, I may have confused some people. I'm talking about layers, drivers, and arrows. So I made a graph. Basically, I just want to point out where things kind of exist in this ecosystem. I put a lot of work into cleaning this up. If you notice something's missing or the arrows don't all connect, I did my best. It was really hard to get graphiz to work. But here we have the green block, SoapSDR in the middle. And we can see how we can build applications on top of it. We have cubic SDR, for example. We can see where SoapSDR ties into Reusable SDR. We can also see where I brought it into Pothos toolkits to get source and sync SDR blocks there. Now this box of purple is essentially most of the modules out there. There's of course more, and these are things you would optionally install if you wanted to support a particular piece of hardware. And there we can see Skylark Wireless, that's my company. We can see how Lime fits in there. We have something called Soapy LMS, and it's sitting with, you can see LimeSweet. The blue is basically a C drivers column. And those two things are actually bundled together here. Although in most cases, all these blue columns are typically bundled separately, but we could put them together. And then you can see how UHD fits in. We have UHD going into several GNU Radio APIs, as well as the SOAP UHD. And here we can see how in the UHD plugins, UHD SOAPy also fits in there, and that's how we close that loop. So can anyone think of a device that's kind of like an SDR? It has a sample rate, but it's really slow. It's an audio card. Now, I just wanted to find a similar graph for the Linux audio system, and this is kind of a famous graph. Now, don't judge it too much. I spent a lot of time making my arrows, but you know, Linux audio is no stranger to abstraction layers, and it looks as if anytime someone wanted to support audio, they made their own layer. And I mean, I think that's fair. You know, we have a few things here. We have SoapSDR, we have GNU Radio, but to me, this is sort of like, where do we draw the line? What's good practice? Maybe they went a bit overboard. So I'm just saying there's a balance here. I think I tried to fill a niche in the ecosystem. I think sometimes this paradigm can go a little too far. And the other interesting thing is this entire chart actually ties in to here. So it's part of one much bigger rat's nest. In fact, audio ties into a number of places within the SDR ecosystem. Just a little story of interest. So finally, I want to talk a little bit about LimeSweet, because I'm here representing Lime. So first of all, I got to say that LimeSweet is here to support the Lime SDR, but it's actually much, much more than that. We have a number of other devices actually supported inside of the LimeSweet right now. There's PCIe-based boards. There's a RF board for using the LMS 7002M RFIC on the Open Novena laptop. There's some other stream and eval boards supported as well. But we've also, it's not just one giant C glob to support all this stuff. We've actually made an effort to sort of architect the library so there's different reusable components. Because basically, we want you to be able to reuse as much of this as possible in your own device. So LimeSweet basically has a similar API to do settings on the device, but with the Lime RFIC, and to enumerate devices. So basically, anything supported under LimeSweet is going to have what comes with it: a high-level C API. We got Python 2, automatic support under SoapSDR, and therefore the entire stack, including Reusable SDR. That's brought in under the Soapy LMS block. And this actually, unlike many C drivers, this actually comes with a fairly neat evaluation GUI. So we're capable of doing high-level and low-level controls, live FFTs, and you can drill all the way down to the bit and wiggle it around and try to get that perfect response, or so be it. So let's whittle that down some more. So LimeSweet has a fairly robust C API that's capable of like enumerating and streaming and configuring just about any board that's supported under there. We also offer some hardware-specific stuff, so we can do FPGA programming, other low-level controls. It comes with a GUI that's tremendous for debugging. You can do I'm having a problem. You can dump all the registers. You can go in and zoom in and wiggle the bits. So this has been an incredibly useful tool for development. And so what we want you to be able to do is, well, our designs are open hardware. Our FPGA designs are open. We want you to be able to take this design and modify it for your own purposes. So it's possible to plug into LimeSweet. This is why we compartmentalize things and pull them apart so you can make the best reuse out of them. So what we've done is we have a C++ API in this case where you can overload a few calls and essentially tell it how to get access to registers, tell it how to stream. You have a Lime RFIC on here. It knows how to talk to it. It knows how to translation all those register calls into high level, set gain, set frequency, tune, sample rate, all that. And it saves a lot of time because you can just have that working out of the box pretty much so long as it has SPI access. To go a little further on that, you may choose to mix and match things. What are you going to put in your FPGA core? How's it going to connect to the bus? One of the things we have is reusable FPGA cores. So going a little further, if you drop our streaming core into your FPGA, you can reuse the LMS64C protocol. And this is even simpler. You tell it how to get bytes in and out. If it's libUSB, how do we get block writes in and out of it? Or similar for PCIe or whatever. And he's going to be able to, at the driver level, he knows how to form packets in and out, control bits, register packets, streaming, whatever it is. And in the FPGA level, he knows how to interpret that. He knows how to interact with the high-speed data IQ lines. He knows how to do controls. He knows how to talk to the RFIC. And you get all of that. So if you can reuse these parts, it'll work in LimeSweet. You'll have this excellent debug GUI. And it just works. SoapSDR, the whole stack, it's there. So I hope you get a lot of reuse out of all these great open hardware and other open firmware and FPGA designs. A few other items of interest with LimeSweet. We have a Python driver, which is pretty cool. I love Python, and I think a lot of people here do too. And so someone was nice enough to make a scalar vector network analyzer example on top of Python. Basically, we wanted to show it off, and you can see a Smith chart there that was generated by the LimeSDR. Also, in tandem with this development, at Skylark, we've produced an open source embeddable C driver. So, if you're not into shared libraries or you need something very tiny, in this case, we needed to fit something into a kernel. We created a C driver. It's not as exciting, of course. It doesn't do high-level streaming. There's not a lot of extraction. But essentially, if you tell this tiny driver how to talk to SPI, he gives you higher-level C calls for all the most important stuff you need on the board, like tuning, setting sample rates, and other configuration like that. And the driver is available on Myriad RF. All right. Finally, I'd like to talk a bit about some of the packaging efforts we've done at Myriad RF, because we like to be able to bring you, in whatever form we can, all of these great driver and SDR stacks, all the way from the low-level C drivers up to GNU Radio. And this isn't just about LimeSDR. We try to package everything in that chart, basically, every C driver we can, and sort of any GNU Radio project that gets requested. So we have three major efforts going on. And one of them is using Launchpad, which is an Ubuntu service to package debs. Another are Ubuntu snaps, which I'd like to get into about how we can create a transactional package and share an entire software stack. And finally, we have a Windows installer that I've created that we host over at Myriad RF that sort of brings everything in that chart as well into a single installer. Let's talk a bit about software packaging. So this is specific to Ubuntu, but I noticed at some point that Ubuntu is always out of date in terms of packages. Does anyone else notice that? So you have an older Ubuntu release, and at the time it was released, it had the latest version of GNU Radio, UHD, you name it. Gets a little stale over time. And I kind of noticed that it was difficult, and I said, let's have a repo with like a PPA with the most up-to-date drivers, the most up-to-date GNU Radio we can. And I fished around a bit, and I noticed Alex from GQRX had a little microcosm of this, where he was actually personally maintaining a PPA with a whole bunch of drivers and just basically in GNU Radio just for GQRX. I said, hey, I think everyone can use this. I could certainly use this. I'd like to basically expand on this. So let's take this over to Myriad RF. Let's make a really up-to-date repository for all the Ubuntu releases and LTS releases. Let's put GNU Radio on there. Let's put drivers on there. Let's put SoapSDR on there. Let's put all the modules I worked on with SoapSDR as well. And so we have that now. Special thanks. He's great help. If anyone's interested in using these, you got the PPA up there, please use them, please test them. Make requests. When new stuff comes out, you know, Alex, he tries to get the latest stuff uploaded. He tries to get the latest branch of GROSMO-SDR with everything in there. We basically need people to help test, say if there's a problem, say, hey, did you notice this new package? Let's put it up. So we're trying to keep that maintained as best we can. I love Ubuntu debs, but sometimes they can be difficult. And so I want to complain a little bit about bad debs too. Has anyone ever installed some Ubuntu packages and left a lot of stuff in user local and then there was some seg fault and you never knew why? Happens to me all the time. Yeah, it's just rm-rf user local. It solves all the problems. But these are things that can happen. Debs aren't perfect. They're meant to be installed in user local and stuff can interfere if it's in your library path. And you know, dependencies sometimes are missing and things can be difficult. You know, we try our best to keep packaged up, but sometimes GNU Radio pulled in a new library. What do we have to do? We have to backport all the dependencies. So it can be hard. And if you mix and match PPAs, like if you use this PPA up here, it's built on a really new version of UHD. You're going to also have to add the Edis PPA or it'll seg fault. So debs aren't perfect. They have some of these problems. So what I want to talk a bit about is another thing from Ubuntu. Oh snap, it's Ubuntu snaps. So what is a snap? It's essentially a blob that has an entire software stack in it. And you can share it, you can install it, and you'll get basically everything you needed to run that, and there won't be any conflicts. It lives in a little compartment. And so, and snaps are also transactional packages, which means you can install a new one, you can remove them. They're very good about cleaning up after themselves, so you never get conflicts between multiple versions, and you're able to swap between them. So, I mean, this is actually great because anyone here can essentially make a snap, share it with someone, and give them an entire software stack without worrying how it's going to work on their particular machine or crash. Building a snap is as simple as a single YAML file. Does anyone here like YAML? It's better than JSON? I don't know, but you basically say, hey, I want to build this project, here's its name, here's all its dependencies. What are dependencies? You can use packages from PPA that are already in Ubuntu. You give it a list of GitHub projects, particular branches, because you may need a very specific version of something, and say Snapcraft, and it builds. It'll build everything from source that you need in there, pull it in, and give you a .snap file. And these are easy to deal with. There's a single file I can put on a USB stick, I can share it, I can put it up on a web server. There's also an option to share it through Ubuntu. They have a Snap store. We actually have LimeNet. With Lime, we want to make it easy for people to upload packages and share them. It's not necessarily a store. You can put completely free packages on it. It's just a place to share it and let Ubuntu do the hosting. So what I've done with snaps is over at MyriadRF, we have the Snapcraft sandbox. It's got a ton of examples, basically using LimeSweet and GNU Radio and SoapSDR software stacks. It's got 3 major different types of examples. So we have graphical examples, which means if you want an app like GQRX, it has all the examples to basically not only build what you need, but to put like the nice icons and the launchers in. I'm very detail oriented. We also command line style examples. So, hey, I need to build this app and I just need the utility I'm going to run. You can do that too. And server style, which is actually neat. You can, let's say you're using Soapy Remote, you can install this package and what it does is automatically launch the service for you. As long as that package is installed, it's actually running the server it was built with. It makes it very easy. You don't have to set up any init.com files or anything like that. It's all expressed in YAML. And then finally, moving on to the evil side of things, I'd like to talk a bit about a Windows installer I've been maintaining. You know, sometimes we have to use Windows. Now my goal here was basically, I wanted to put everything in that giant graph into a Windows installer to make it easy to point, click, install, and run stuff. This is no easy challenge. At this point in time, nearly everything's in there. We have something like 60 software packages that we're building from source. You know, entire GNU Radio, entire GQRX, some GR Star projects, everything I did with Pothos, everything with LimeSweet, everything with SoapSDR, lots of dependencies like GSL. I try to build as much as I can. It's basically a big CMake project, so it's totally open. Anyone can take it and modify it and add stuff too. So we just, with a lot of CMake external projects, we give you the Git branch, we give you the version, and it's able to build this. We've actually been able to keep the installer under 80 megabytes, which is a big thing I wanted to do. I was like, I want to keep this small. So Basically, that meant we didn't ship Boost development files and Qt development files and some Python, and that keeps it down. So this is all the development files and development libraries you'd ever need with this entire ecosystem, with the exception of Boost, because depending upon your use, you might not need Python. So you can install this. Thing. Maybe you have to put in a driver for your SDR. We have a tutorial on that. Go to the Start menu and click GQRX. It's just going to work. It just opens. The launch is all set up. But if you're going to do something else, like maybe use GRC, you might need some particular Python dependencies, like an interpreter. Or if you're going to develop against GNU Radio blocks, yeah, you have to go grab Boost and install it. It's really big. It's like a gig. I didn't want to ship the same Boost with every single installer. I make these once a week. We try to be very detail-oriented here. So this is the idea is to be a one-click wonder. So everything we can try to set up beforehand, we do. So when the installer runs, we have Python modules for GNU Radio. We have Python modules for SoapSDR. How am I at? So we make sure we set the Python module path. So as soon as you install it, boom, you can import Python from GNU Radio and etc. We also did everything we could to set up like launchers and stuff. So this means all the icon associations work. You can double-click the save icon. It'll open GRC. I basically put a ton of work into this personally, and I've watched Swig compile way more than I ever wanted to, so I just wanted to share the amount of effort that sort of went into this. And sort of debugging here was like real pain. I remember way back when GNU Radio, someone type-defed a pointer to long, and that's 32 bits on some 64-bit machines, and it was just crashing, and it took me all day to figure that out. I also really like to thank I believe it's Jeff now who maintains the Windows installer. He's been tremendous to like upload tons of stuff and also help in keeping GNU Radio maintained under Windows. It's been really a big deal. I also want to mention I made a little clever GNU Radio companion launcher just for this project. So it's an EXE that actually loads the underlying Python, but it sanity checks your environment. So if you're missing modules, it'll go fetch it if you don't have particular environment variables set up. So we really wanted to get the one-click thing working. So anyway, check it out. Sorry to bore you about Windows. We have a tutorial. We also have a link to GNU Radio, so you can set that up from there. So that's my talk. So in summary, SDR is built on a diverse set of drivers and APIs churning under the hood. I hope I sort of open that world up a little bit. SoapSDR is a cool and versatile tool for the SDR community. I hope it actually solved a niche or a problem here. It certainly did for me and some of my developments. LimeSweet is there for anything using the LMS 7002M. It makes it really easy to develop applications and reuse as much code and hardware as possible. And finally, we have a number of packaging efforts over at Myriad RF, PPA, snaps, and Windows installers. I hope you make good use of them. Thanks for watching, and just questions or comments if there's any time left.
Yeah, we do have a few, and we already have some hands up. All right, Jose, can you get to Nathan? And actually, Michelle, if you want to come and start getting mic'd.
So I'm not real familiar with all the different Snap and Docker type container things. Why would you choose snaps, or what advantage do snaps have over the other?
Oh, I thought I'd get asked for this. There's a lot of options out there. This is one that I picked and just learned and wanted to share about because that's sort of what we went along with. I'm sure Docker's good too. I'm just a big fan of Ubuntu stuff, and this is something we were working with Lime and LimeSDR, Myriad RF, and we just went ahead and did snaps. For what it's worth, they're pretty easy.
Any other questions? I've got a couple. You talked a little bit about licenses. Talk about the license for, I think, Soapy. What's the license for LimeSweet?
Apache 2.
Apache 2. Okay. And then my second question, actually kind of along the same lines as Nathan. Do you really see a difference between, this is more the container question, GNU Radio, right, we talk a lot about installation and how to make it easier. So it looks like you've done a lot of work with snaps. Do you have any thoughts on how those might be applied, either snaps? I think the GNU project has their own version called Flatpaks, right? And then there's obviously Docker. Do you have any thoughts on how that could be applied to GNU Radio?
Well, so I think the main idea of a snap is I try to think of it as an application or a particular use case. So whereas when I made the Windows installer, I tried to package everything in there I could, you're really building a snap for one case. And it's not necessarily even meant to work for everything under the sun all at once. It's containerized, it has certain protections. It doesn't really want to do that. In fact, you may have an issue creating like simultaneous WX, Python, and like Qt launchers for all the stuff. So Yes, if you have an app you want to share with someone, in this case. I actually think it's not that applicable for doing, I want to share a development library with you. That's a little bit different. I want to share an app, and a lot of people do want apps. You know, they want to be able to launch something. Whether it be just GRC and I want to design and make Python, that's actually very applicable. And we do have a snap for that.
Okay.
Or GQRX too, right?
Cool.
Things of that nature.
All right, any other questions for Josh? No? Oh, we have one more. And
He said it.
sorry. Oh, did I? With 1 minute left. Sorry, I should have pointed better.
Sure.
Just like you said, sometimes we have no choice but to work with Windows. The Boost libraries are a pain. I could tell you, as you know. There's a TX99 has a precompiled DXE, so I was just wondering if you can pull those in.
Precompiled EXEs for Boost?
Yeah, on Windows.
I believe I am using them.
Yeah, I know too, but you're saying you don't pull them into the
I
install. I was just wondering.
I don't.
It's nice to have everything in Windows just to work because it usually doesn't.
So we ship the Boost runtime libraries. What I don't ship is the .libs for development and the headers. And I mean that they're really, really big. I just.
No, that's fine. Okay.
But I tell you what version of Boost, and you can actually go download it. And there's always a little bit of work if you're going to go compile something because you have to point to the right headers and all that. But
okay.
that was the trade-off essentially.
Yeah, no, it's good. Sounds good. Thanks.
All right, thank you, Josh.
Cool. Thank you.